Dear all the audience, and my name is Fengyi, and it's my honor to be here to present our latest work on WCV, is that RPCANet deep unfolding RPCA-based enforcement target detections, and we are from the University of Electronic Science and Technology of China and cooperate with the University of Copenhagen. And before we get to our methodologies, we give a brief view about the background of enforcement target detection. We define an enforcement target as occupy less than 81 pixels or less than 0.5% area in an image which is lacking in shape and texture informations and is disturbed by background clutter and arbitrary noises. And in the past few decades, a lot of model-driven ISTD methods have been emerged, such as filter-based, HVS-based, which is shortened for human vision system, and the popular one is optimization-based, which treat the background low rank and target sparse. So for the model-driven approaches, it has its pros, such as it has theoretic and physical foundations, and it has interpretable detection results. However, it is heavily reliant on fine-tuned patterns and not suffices when environment change. And with the emergence of deep learning, the object detections approaches has been directly applied on the ISTD, but it has relatively poor results because they ignore the huge gap between the visible light and the infrared imagery. So a lot more researchers have treated the ISTD as a segmentation test because it can better capture discriminative and solid features. However, it's pre-trained on the image-less constrained infrared data representations, and multiple downsampling triggers the target loss. And we, as nowadays with more knowledge on deep learning, it has also treated as black box. So we have to sort out how that if there is a balanced approaches that could combine the merge of data driving and model driving, and here comes the deep unloading ways, which unfolding the optimization steps into the deep frameworks, and it has been greatly applied on the image reconstruction, removal, and shadow removal, and that's where we start. So before we get to the deep work, we first do some problem modeling. We separate the infrared image into a background and target and model it with RPCA. And instead of using the traditional width as a nuclear norm plus the L1 norm, we roll it back on a relaxed RPCA model and turn it to a unconstrained problem as shown in the last equations, and we do some model iterative solving. And also we present some normal ways, such as using the SVD decomposition to exterminate the background and extract the target using soft thresholding, but we find the calculations are too complex, and we directly use a approximate operator to describe the estimation weight of background, and we suppose the sparse constraint of target is Leibniz continuous, and we can use the Taylor expansion to describe these formulations and turn the closed form into a directly sum way. And the inconsistencies with the RPCA steps, we update the original image as a compilation of two background and the target. So we can see our model iterative solving ways has no complex metric operation and is simply sum of two L2 norms, and the whole procedure is under Leibniz continuity assumptions. Based on this, we are unfolding them into the deep framework. For the background, we design a background expectation models, and after we search different networks such as restless plus research construction, we find the most efficient way is to directly use the residual construction, and the framework is shown as the figures. And for the target extraction model, we inspired by the 2018 NIPS paper is that once the function is Leibniz continuous, we can use neural network to emulate it with the convolution plus the ReLU layers, and this is how the frameworks of the target extraction model looks like. And also we adopt a fast and flexible FFDNet to conduct the image reconstruction test. And here is a single state structure of our framework. And you can see it's a combination of BM, TM, and IRM. So like most deep unfolding framework, we use different stages to design the end-to-end training framework, and the learnable parameters is shown as the parameter set. So we conduct a lot of experiments on our frameworks, and here are some experimental details. And it is noted that for the training loss, we separate the task into a segmentation task and a reconstruction task. And we adopt 3 different public data sets. And before we give you some numerical and qualitative result, we first verified our models. As you can see in the background, when the stage as an early stage, the neural network just learns some strong edges, but when the stage gets deeper, the learned features has been closer to the low rank, and as to the target, it has also learned some strong edges features in the very beginning, but when the stage gets deeper, the target has been more sparse and eliminate some sparse-like targets with the mask-guided informations. And also, we do some numerical tests for the low rank. As we can see, when the stage gets deeper, it has a richer informations, and it has also keeping the low rank feature. So we also compared our framework with some optimization-based PSTN, and we can see when the stage gets deeper, it's still keeping the sparse feature and learn the mask info, which eliminate the false alarm like in the PSTN. And compared to our RPCANet, it's clean and well detected. So here is some qualitative results on 3 different data sets. As we can see, our RPCANet detects the target accurately and eliminates the false alarms. Also, the numerical performance on 3 different datasets show its competitive results of the target level and pix level matrix, and it has light parameters and run fast in the running time matrix. Here is the ROC curves of it, and you can see our method is quite competitive. And we can see that overall of our construction is that we model the framework, deep framework, basis on the mathematical equations, and we call it ad hoc. And what we do, such as the sparse test and the low rank test, which is a postcard, and postcards plus ad hoc is really close to an interpretability framework. So we have a discussions on our RPCANet is that first of all, we'll give it the conclusion that we built a RPCANet that's combining accuracy of data-driven and interpretability of model-driven approaches. Complex metric calculations and parameter fine-tuning procedures are replaced by neural networks. And our RPCANet guides the neural network to learn the low-rank background and sparse target in almost white box architectures. In the future, we will improve it in different models, and we would like to share to our field researchers that say hi and embrace to deep unfolding. And thank you, and that's all. And feel free to contact us at our emails.